Turning to disjunction, we again have two rules. We have a restricted disjunction rule, which we can use whenever that restriction, that limitation holds, namely that the two events are mutually exclusive. So it's like exclusive or exclusive disjunction. What's the probability of one being true or the other being true when they both can't be true at the same time? So when we know the two events are such that only one of them can happen, we can calculate the probability of disjunction using our restricted disjunction rule. And it tells us that the probability of A or B equals the probability of A plus the probability of B. So let's go ahead and do an example to illustrate how we'd use this rule. Let's calculate the probability of drawing either a spade or a club on a single draw from a shuffled deck of cards. So we know that those events are mutually exclusive. We draw one card from a deck. We know that it's either going to be a spade or a club. Can't be both. And so those two events would be mutually exclusive. And so we can use our restricted disjunction rule. There are 4 suits in a deck. They each have the same number of cards in a suit. And so we can use our classical theory of probability to estimate the probability of the individual simple events. So again, we start off by estimating those simples. The probability of drawing a spade, 1 out of 4. Right? Every deck, 4 suits, equal numbers, 1/4 of the deck will be spades, so 0.25. Same thing with clubs, 0.25. We enter those values into our equation. The probability of drawing a spade or a club is going to equal 0.25 plus 0.25. We then perform our calculation, adding those together, and we discover that the probability of drawing a spade or a club is going to be 0.5. Now you might wonder, why are we adding now? We were multiplying for conjunction. Why are we adding now for disjunction? And the answer has to do with, again, how you add fractions. And again, we can illustrate it talking about rolling a die. So say we want to calculate the odds of rolling a 6 or a 4. Now each outcome, the 6 and the 4, are a possible way that the world might turn out. There are 6 possible ways. Our 6 and our 4 are 2 favorable outcomes, but adding a favorable outcome in this case doesn't change the total number of possible outcomes because we have that strict number. We have that 6 sides of our die, and now we're just specifying more than one favorable outcome out of those 6. And so when we think about how we add fractions, right? When we add our probabilities, what we in effect do is add the numerators of our probabilities expressed as fractions. In this case, 1/6 for one outcome, 1/6 for another outcome, 1 plus 1 equals 2. And likewise, we keep the number of possibilities fixed because when you add fractions, you add them using a common denominator. You don't change the denominators other than to make them the same. And so they remain constant, and hence we have a denominator of 6. And so we get 2 possibilities that are favorable and 6 total possible outcomes when we add our simple probabilities. What about our general disjunction rule? Well, our general disjunction rule corresponds to the wedge in propositional logic. It is inclusive or. It can be true if one is true, or the other is true, or they're both true. And to calculate the probability of a disjunction when the mutual exclusion restriction doesn't apply, we use the general disjunction rule. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And that would be just the multiplication of the probability of A times the probability of B. So let's use an example to show how this would work. Suppose we want to compute the probability that you're a freshman or a male. So some freshmen are males, some males are freshmen, so it's possible for both of the disjuncts to be true. So we'll start off by estimating our simples. Again, we could probably use the frequency interpretation. Freshmen are about 1/4 of the population, about 0.25 of undergraduates. The population of males is slightly lower than the population of females in the university, so maybe about 0.3 or 0.43, excuse me. And now we plug those into our formula, and we now say that the probability of A or B, given that they both could be true, is 0.25 plus 0.43 minus 0.25 times 0.43. We perform our calculation, and we get the probability at 0.5725. Now, you may wonder, why we have this strange formula all of a sudden? Why is it that we're subtracting the probability of A and B after we add the two simple probabilities together? Well, if they can both happen, then when we look at what the probability of A is and what the probability of B is, we see that they really have two components to them. They have the probability of A being true but not B, and the probability that they're both true. Those are both ways for A to be true now because they're not mutually exclusive. When we look at the probability of B, it's the same story. We have the probability of B and not A as one way B can be true, and the probability of A and B as another way that B could be true. So when we add them together, we realize that we'd be adding the probability of just A being true, the probability of just B being true, and then we'd be adding the probability of A and B being true twice. But it's only one possibility. It's not two possibilities. And so we could state a rule like this: the probability of A and not B plus the probability of B and not A plus the probability of A and B, one or the other or both. Or we could add them together. We've got two now, but we just subtract our second A and B. And that's what we get with our formula: the probability of A and not B, and the probability of A and B, plus the probability of B and not A, and the probability of A and B. And we get rid of an extra probability of A and B by subtracting it out again. Our last rule is the negation rule. And the negation rule takes advantage of the fact that that the probability of all possible outcomes is always going to equal 1. There's something got to happen. So the probability of any event, A, is going to equal 1 minus the probability of A not happening, whatever that involves. And so we can sometimes use this negation rule to calculate the probability of an event when it not happening is simpler to calculate than it actually happening. So the probability of drawing a club or a spade or a heart from a poker deck on a single fair draw would be a nice example of this. If we wanted to calculate the probability of that, right? Well, the probability of being a club, a spade, and a heart are each 0.25. There are 4 suits. They're each 1/4 of the deck. And then we think to ourselves, okay, now we're going to have to calculate all those different simple conjuncts into our total conjunct of a spade or a heart or a club. But we could just realize, hey, there's only one more suit. We know what that probability is going to be. The diamond suit will be 0.25, just like all the others. And so it would be easier for us to calculate the probability of this clubs or spades or hearts by taking the probability that I get a suit, and subtracting not getting one of those 3 possibilities, i.e. a diamond, 0.25, And then when we do our calculations, it's 0.75. Now you can use the disjunction rule, exclusive disjunction rule, restricted disjunction rule rather, to get that same number by adding each of these up. But when a problem starts to get complex, you can consider using the negation rule as a way of simplifying how you calculate the outcome.